Somewhere at the outer edge of our solar system, a planet is hiding a secret so strange that scientists still cannot fully explain it. It is bright blue. It is bigger than Earth by a factor of 4. And deep inside it, under pressure 7 million times greater than anything on our planet's surface, carbon is being crushed into diamonds. Real diamonds. Falling like rain through a superheated ocean of liquid slush, drifting past icebergs made of solid gemstone, sinking toward a core the size of Earth itself. This is Neptune. For most of human history we did not even know it existed. It cannot be seen with the naked eye. It sits nearly 4.5 billion kilometers from the Sun, a distance so extreme that if you compare it to Jupiter, the fifth planet from the Sun, Neptune is not twice as far away. It is not 3 times as far away. It is 5 times further from the Sun than Jupiter is. And yet this frozen, distant world is not calm. It is not quiet. It is, in fact, the most violent place in the entire solar system. Winds tear across its surface faster than the speed of sound, 5 times stronger than the most powerful tornado ever recorded on Earth. A storm the size of our entire planet once raged across its face, spinning with winds that were clocked at nearly 5 times the strength of any hurricane humanity has ever measured. Only one spacecraft in history has ever gone close enough to see it. It arrived by accident of timing, using a rare alignment of planets that happens only once every 200 years. What it found would rewrite everything scientists thought they understood about the outer solar system. This is the story of Neptune. A planet built on pressure, heat, and chaos, hiding secrets that even now, decades later, we are still trying to unravel. Neptune and its neighbor Uranus belong to a category of world scientists called the ice giants, and together they represent the least explored region of our solar system. Only one probe has ever traveled through that region in the entire history of space exploration, NASA's Voyager 2. To reach that far, Voyager 2 could not simply fly in a straight line. It relied on a planetary alignment that comes around only once every 2 centuries, using the gravity of each gas giant to sling itself forward toward the next, until it finally reached the very edge of the known solar system. Neptune's discovery did not come from a telescope pointed at the right place by chance. It came from mathematics. Astronomers had noticed something odd about the orbit of Uranus. It wobbled, as though some unseen force out in the darkness was tugging at it. A mathematician named Urbain Le Verrier used physics to calculate exactly where that hidden force must be. When astronomers finally pointed a telescope at his predicted coordinates, they found Neptune staring back at them. That was 1846, making it one of the only planets in our solar system discovered through calculation before it was ever confirmed by sight. For over a century after that, almost nothing more was learned. Neptune was too dim, too distant, too faint for the telescopes of the era to reveal anything beyond its existence. Scientists could guess that it was cold. That was about all. It would take until the late 1980s, when Voyager 2 finally arrived, for humanity to understand what kind of world this really was. Before Voyager 2 reached Neptune, it first passed by Uranus, and what it found there set expectations for what might be waiting further out. Uranus turned out to be eerily still. Pale, smooth, and seemingly frozen in place, with almost no visible activity anywhere on its surface. It was a beautiful discovery, but a quiet one, and it left some scientists wondering if the most interesting parts of the solar system had already been left behind at Saturn. 3 years later, as Voyager 2 approached Neptune, everything changed. The spacecraft itself was not built for this. Its instruments were, by the standards of a modern encounter, primitive. It carried wide-angle and telephoto cameras fitted with color filters, along with sensors that could read infrared and ultraviolet light to measure temperature and density, plus tools built to detect invisible forces like magnetism and radio emissions. It had been engineered decades earlier with one priority above all: survive long enough to make it this far. The first thing its cameras captured was a color unlike anything else in the solar system, an electric, saturated blue. And as Voyager drew closer, it became obvious almost immediately that Neptune was nothing like its quiet neighbor. This was not a calm world. This was a world of violence. The wind speeds recorded on Neptune remain the fastest ever measured on any planet in our solar system, roughly 5 times more powerful than Earth's strongest tornadoes, with gusts capable of breaking the speed of sound. Scarring its surface, Voyager spotted a storm system as large as Earth itself, later named the Great Dark Spot. It rotated counterclockwise, much like the Great Red Spot on Jupiter, but inside it, wind speeds were recorded at over 2,400 km per hour. To put that in perspective, the strongest storms ever measured on Earth top out at around 500 km per hour. Neptune's storm was moving nearly 5 times faster. Much of this detail was only visible because Voyager 2 came within roughly 5,000 kilometers of Neptune's cloud tops, the closest approach the probe made to any planet during its entire journey through the solar system. And that flyby exposed a genuine mystery. Wind, in its most basic form, is created when hot air collides with cold air, and the greater that temperature difference, the more violent the wind becomes. If Neptune's winds were the strongest in the solar system, that meant something down there was generating serious heat. It could not be the Sun. Neptune receives only about 1,000th of the sunlight that reaches Earth. Given how still and lifeless Uranus appeared, scientists expected Neptune, sitting even further from the Sun, to be even colder and even quieter. Instead, its clouds were both more active and slightly warmer than Uranus, a temperature difference of only about 10 degrees. But because Neptune sits 50% further from the Sun than Uranus does, that small temperature gap actually points to an almost unfathomable internal heat source, something generating warmth from deep within the planet itself. To understand where that heat comes from, we have to go beneath the clouds. Neptune is not as dense as a rocky world like Earth, but compared to the other giant planets of the outer solar system, it is the densest of them all. Density, in this context, means pressure, and pressure is the key to everything happening inside this planet. At the outer layer sit thick clouds of hydrogen, helium, and methane. It is the methane that gives Neptune its striking blue color because methane absorbs red light from the Sun while reflecting blue back out into space. Beneath that cloud layer lies a thick mantle, a mixture of water, ammonia, and methane blended into a dense, slushy mass that makes up most of the planet's interior. At the very center sits a solid core of rock and metal, roughly the size of Earth, but around 50% heavier. The immense gravity of that core compresses everything in the mantle above it into an increasingly hot, dense soup. The closer you travel toward the center, the greater that pressure becomes, until something remarkable happens. Neptune's abundant methane is rich in carbon, and when carbon is subjected to extreme enough pressure, it begins to crystallize. Those crystals are diamonds. Deep inside Neptune's mantle, under atmospheric pressure roughly 7 million times stronger than what we experience on Earth, methane is believed to be compressed directly into solid diamond. These newly formed crystals then fall like rain, sinking deeper into the planet until they reach a liquid so dense that even solid chunks of diamond can float on its surface like icebergs. It is the friction created